So the binomial theorem is looking at if we did binomials to different powers, what happens? Well, we've done some of these already. The easiest one, to the power of 1. A plus b to the power of 1, if you had to simplify it, would be equal to a plus b. Another one that you have done already is squared binomials. What would you get if you squared that binomial? Well, it would be a plus b times a plus b. A squared plus 2ab plus b squared. And if you had, I'll do it, a plus b cubed, well, that's a plus b times a plus b times a plus b. And we already know that that is a squared plus 2ab plus b squared. And if you multiply that by a plus b, this a would get distributed to each of these. This b would get distributed to each of these. And if you multiply that out and combine like terms, you would get a cubed plus 3a squared b plus 3ab squared plus b cubed. And then you could use that result to find a plus b to the 4 and have to distribute all of that. And then we could find a plus b to the 5. But I'm going to get you to tell me what these next ones are without having to multiply it out. What do you think a plus b to the 4 will be? A to the power 4. A cubed b plus 6 So what patterns are we noticing? I mean, I could have added green numbers in front of here and here, right? There's Pascal's triangle. Okay. And even if you went back even further, what exponent didn't we do? A plus b to the 0, that's equal to 1. So we see Pascal's triangle comes out in the coefficients. What's going to happen? Have you seen a pattern in the exponents? So if we did a plus b to the 5, we would have a to the 5, then a to the 4 and 1b. So notice the powers of A go down by 1, and the powers of B go up by 1. Now, a little explanation. Why is it that Pascal's triangle shows up here? And why are the coefficients of these ones combinations? And why did we connect this? What's so important about connecting this to combinations? Because right now we're doing algebra. And Pascal's triangle appears, but the only connection to Pascal's triangle was it also happens to be combinations. But why are the two related? So if we look at a plus b to the 5, and that's equal to a plus b times a plus b times a plus b times a plus b times a plus b. Whew. Now, in the past, when we multiply this out, what we do is we multiply the first two together, and then you multiply another one, and then you multiply another one, and then you multiply another one, and you keep distributing all the way through. But what ends up happening when this is all multiplied out is, because there's a plus sign in there, when you multiply things out, you're either choosing the A or the B in each of them. So when you want to get a term like, I'll square that in red. Here we go. When you want to get this one, it has to have 3 A's multiplied together and 2 B's multiplied together in order to get an A cubed B squared. So we have to decide in these 5, which 3 A's are we going to choose and which 2 B's are we going to choose? And as far as matching it up perfectly with our choose thing that we found out earlier, we'll talk about how many B's we're looking for. Well, I could choose this B and this B. Or if I wanted 2 B's, I could have chosen this B and this B. Or I could have chosen this B and this B. Well, how many ways could we choose 2 B's? There's 5 B's to choose from, and we need to choose 2 of them. And that 10 in front is 5 choose 2. How many B's are in this one? There's none. This is 5 choose 0. And this one, there's 1 B. It's 5 choose 1. And those numbers that we wrote out in Pascal's triangle as far as combinations, this is the reason behind it. Because when we're expanding this, we are choosing which B's. And you know how combinations are symmetrical, like 5 choose 4 is the same as 5 choose 1? And so I used choosing B's here because I wanted it to match up 5 choose 0, 5 choose 1, 5 choose 2, exactly as we wrote it out in the triangle before. But we could have said, instead of choosing B's, how many ways can you choose 4 A's? So then this would be 5 choose 4. And the numbers would be the same. But just so that it matched up with what we have here, and this is also going to match up with the formula you have on your formula sheet. Now on your formula sheet, it looks like this. Now that'll disappear later. Okay, on the formula sheet it says 4a plus b to the n. Make sure they didn't use x and y. Oh, they didn't even say 4a plus b to the n. I'll add that in. They just give you the next part. But it's important for the first time that you see that. When you have a plus b to the n, then we get the following. Okay, first of all, the tk plus 1 stands for a term. When you do an expansion, like we did here with all of these, for this last one, I would call this term 1, this my second term, term 2, this term 3, this term 4, this term 5, and this term 6. So when we're trying to find a term, and in the formula, it has tk plus 1. So it's a weird formula in that it has one more than a variable already. It's so that when we look at, for example, which one did we square? We squared term 3. Can you see that the coefficient in front of term 3 is 5 from the exponent? Choose 2. And that 2 is 1 less than the term position. And we saw that when we looked at Pascal's triangle, that it was always 1 less than the term position. We actually really, we also noticed it was 1 less than the row, but once we get into this, we're really not concerned about the row number, but we will be concerned about the term position, and the k value is always going to be 1 less than the term position. And so that shows up in the formula, because if I wanted to find term 3, then can you see that k would have to be 2? So we go 2 plus 1 makes 3. That would make term 3. And so k is always 1 less than the term position. So the n choose k becomes our green number in front. And then we had the variable a, which is the first one. How many did we have? Right? When we had the third term, we had 3. When we had the second term, we had 4. When we had the first term, we had 5. How are we going to figure out how many there are? Well, again, we're going to look for a relationship between this exponent and n and k. So look at n and k. For the first one, we have a 5. N is 5, k is 0. For the second one, we have a 4. N is 5, k is 1. For the third one, we have a cubed. N is 5, k is 2. So when we go to our formula, what are we going to write for the exponent for a? N minus k. A is whatever is the first term. Yeah. Yes, it'll be just like when we expanded it, it's a number times by a to an exponent times by, and then we have b. And again, look at n and k. What is the pattern for the exponent for b? It's just k. Can you see that here the 5 choose 2, but the b is always 2? Because that was what we were choosing. We were choosing 2 b's, or we were choosing 1 b. So that explains why that is the exponent there. And so this formula finds any term in a binomial expansion. What's nice about it is you can quickly find, right, faster than we probably could before. If you wanted to find the 7th term, if you had a plus b to the 15. Can you imagine multiplying that all out by hand, combining all your like terms, and then figuring out what the 7th one is? And this gets it to you right away. Some other important observations that we can make from our binomial expansion and from this formula. There are always n plus 1 terms in the expansion. So notice in our 5th one, if we count how many terms we had, we went up to term 6. So when you have a plus b to the 5, you have 6 terms. Now, there are so many things that you run into math where sometimes it's 1 more and sometimes it's 1 less, right? Because k is 1 less, but there's 1 more term. And when you have a lot of things like that that are similar but different, that's when your memory starts to falter, right? And you start to go, oh, is this one 1 more? Is this one 1 less? And sometimes you're on an exam and you're like, I can't remember, I'll just guess one of these. Well, usually that guessing is about 50%. If you're guessing between 2 things and one of them's right, you're usually going to get it right about 50% of the time. So it's not necessarily the best strategy. What I like to do is when I forget or I'm unsure, I go back to a simple case and think about it. And the simple case, a plus b squared. You've squared so many things by now. How many terms are there going to be? You know there's going to be 3. So then that helps you remember that, oh yeah, when you expand, there's always 1 more. It's 1 less for the k. So those are some strategies you can use when you have things memorized, but you start to get that, oh, I'm a little bit unsure. Go back to a simple example to check which of your hypotheses is actually correct. So we already talked about this. K is one less than the term number. Mumber? It looks beautiful. So our k value is always one less than the term number. There's n plus 1 terms in an expansion, and we can figure out any kind of term. So if I wanted to just find, I'm going to put a purple box around this one. If I wanted to find that purple box, that would be term 3 in a plus b to the 4, right? So the purple one is term 3 in a plus b to the 4. So all we're going to do is we're going to use the formula here just to verify what we already know, that it should be 6a squared b squared. So when we go to our formula, I'll just scroll up so we can see it here. tk plus 1. Well, we're finding term 3 in that purple one. If we're finding term 3 in that purple one, that means that k is going to be 2. The n value always comes from the exponent. So here we're going to get 4 choose 2. We have a to the 4 minus 2 and b to the 2. Calculate 4 choose 2 is 6. 4 minus 2 is a squared, b squared. And does that match up with what our third term was? Yes, it does.